Okay, so before we get back to coloring, so I put the map of the United States on canvas. I suggested, now what you want to do is you want to make a graph out of that. So the graph is created in the following way. Each state corresponds to a vertex, and you're going to put two vertices together, or put an edge between two states, if they share some border. Okay, and you get a graph. Okay, forget Hawaii and Alaska, okay, because they're disconnected. They would just be floating out in the ocean. So we get a graph on 48 vertices. And did anybody think about what the maximum degree would be? So that's something you might want to think about, what the maximum degree is, what the minimum degree is. I mean, there are states that are adjacent to a lot of states, and there are states that are adjacent to very few states. And what I want to do is I want to color the vertices with as small a number of colors so that any two adjacent states are given different colors. Okay, and that's basically the whole idea of the four-color theorem. That it was believed that four colors, it was shown very early, maybe as early in the 1700s, that you needed at most 5 colors. But showing that 4 colors sufficed there were proofs, they were incorrect proofs that existed in the 1800s. There was a proof that actually existed amongst journals for almost 20 years until the mistake was found. And that went from 1893 to about 1920. And then finally in the 70s, it was shown that 4 colors. If you take a map and do exactly what we said, then you can color that with 4 colors. So now let's think about well, what if we don't have maps? What if I'm just looking at a graph? So what we want to start talking about is coloring graphs in general. So I'm going to take a graph G. And what I want to do is I want to color, you're not really going to color it, but we're going to imagine that we're going to assign colors to vertices, color vertices, so that adjacent vertices are given different colors. Okay, so in particular, I'm not going to draw the Peterson graph yet. So if I'm looking at this graph here, better known as the K5, how many colors does it take to color this? 5 colors. Because every vertex is adjacent to every other vertex, I've got to have a distinct color for each vertex. So this whole idea of coloring has really encouraged quite a bit of research and interest among graph theorists. So before we get to coloring, I've got to go back and actually talk about a few of the definitions back in chapter 7. So we won't spend too much time, but let's see, look at page 298. Okay, so by the way, let me just, okay, so we're coloring. I just want you to, as you're thinking about your interest in graph theory and it's interesting. To get involved in some of these coloring problems. It doesn't matter what we color. So for every one of these vertex coloring problems, we have similar edge coloring problems. Okay, so I want to color the edges of K5 so that no two edges of the same color share a vertex. Okay, so this idea of coloring vertices can be extended to coloring edges. And again, no two edges that share a vertex can be colored the same. Okay, so just take a minute. How many colors does it take to cut? First of all, how many edges does K5 have?
4, 10.
Do I? How many? 20?
10.
Yes.
20?
10.
Which one?
10.
You sure?
Yeah.
Okay. All right. So it has 10 edges. I want to color this. Can you color? Let me back up. Can you color the vertices with 5 colors so that no two adjacent vertices are given the same color?
Yes.
That's a pretty obvious question, right?
Mm-hmm.
Okay, same question for edges. Can you color the edges so that no two edges sharing a vertex are given the same color?
Name.
You're all looking at it like it's going to magically color itself. That would be.
You want this lesson in our
Wow, it's quiet.
Well, that's fancy.
5. You think you can do 5?
That's what we need, but we need it on.
I don't have 5 colors. Do it with numbers.
I can hook it up to that.
That would be good.
Okay, Ying thinks she's going to do it with 5 colors.
I have 2 so far, 2 colors.
Oh, okay. Tell her no. Tell her to start again.
Yeah, 2 folders that are vertices.
So
So
I think I
do you
can
have
do it.
one?
Well, these 2 sharing edge.
Motion to, so 6.
So are these 2.
Thank you.
So these 2.
Because I started on the outside and then one on the inside.
No,
I
then
did
the
leave
2
it on the
4
inside.
share an edge. 2
So I
share a
started
vertex.
like this.
Well, I think you can still do it.
Oh, I see. Okay.
So if you made that one that was 4-3, aren't you good then? Yeah.
Uh-huh. Yeah.
You have 1, 2, 4, so that one's gonna be a 2.
No, that's too many 3s. What's left?
2 5.
Yeah.
You will have 2 5.
Tell her.
What? Like I'll be 5. Just,
This
Yep,
one?
yep,
yeah.
and the other one.
This one? 2?
Five.
Five.
Five. Make that 5 clearer. Very good, okay. So I have 10 edges. K5 has 10 edges. And in fact, we note that we can color it with 5 colors so that there's a pair of non-intersecting edges for each color. So I need to define a few things. So I'm going to use his terminology. So let me see. I need to, yes, okay. So alpha of G is the independence number of G, and it's also the order of the largest set of independent vertices in G. Okay, calls that the independence number. That's good because that's what I call it. Now, I'm going to slip sometimes. So now what I would like is, so independent vertices are easy. What do we mean by independent vertices?
Not adjacent.
They're not adjacent. So just hear me out. Let's look at K. Let's look at K34. So just so I know everybody's on at least close to the same page. So what's the independence number of K34? Do what? 4. And where would those 4 be?
The bottom.
The bottom. So it's the set of the largest set, the order of the largest set of independent vertices. Okay? So that's the independence number. I call alpha prime of G the edge independence number. What do you think?
They don't share a vertex.
Do what?
They can't share a vertex.
Okay, so the edge independence number is the order of the largest set of edges. So we're just mimicking this up here. Order of the largest set of independent vertices, largest set of edges that don't share a vertex. So, in essence, the edges are independent. Okay. He calls this the matching number. He calls a set of what I would call independent edges, he calls this a matching. Sorry, they call this a matching, and they call this the matching number. Edge independence number, they call it the matching number. Now, if you were developing graph theory, and you had a matching that matched all the vertices, a matching, so they're independent edges, and it matches all the vertices up. What might you call that? I like to think that graph theory sometimes is just the common sense mathematics. Perfect. Okay, so a matching that covers all the vertices is a perfect matching. Okay, so let's just make sure it's clear. K5 does not have a perfect matching. Is that clear?
It's a matching.
Can someone give me a real quick proof that K5 doesn't have a perfect matching?
We're saying it covers all the vertices because every vertex is adjacent to something in the set or incident.
Older, the larger the set of edges that data share cover all the vertices in a perfect match.
Okay, one more time. Why wouldn't K5 have a perfect matching? It has an odd number of vertices. And if I have a matching, each edge in the matching covers two of the vertices. Okay, so if I have an odd number of vertices, there's no way I can have a perfect matching. So we're looking for the largest set of independent edges. Okay, and I would call this the edge independence number. The book calls it the matching number. Okay. Okay. Now this is the one that I always get confused with. So beta is the vertex cover number, and beta prime is the edge cover number. And there's a reason we're going through this, because we're going to develop, as we develop more about colorings, we're going to use independent sets. We're going to use edge covers and vertex covers to help us find some of these values. So again, if you were the vertex cover number, I can't explain the use of this. But anyway, the vertex cover number, we're covering vertices with edges. So it's the smallest set of edges that covers the vertices. And we're going to do some examples. We're going to go through a bunch of examples. The edge cover number, it's the smallest set of vertices that cover the edges. It's just something that you just have to get used to. Oh well, I mean, you know, I don't know if it's backwards. The vertex cover means that I'm covering vertices. If I'm covering vertices, then I'm probably covering it with edges. Okay, and the edge cover number, I'm covering the edges with vertices.
I think it is backwards. A vertex cover is a set of vertices.
A vertex cover, you sure?
That's how I remembered it when I took this class.
Yeah,
on page
well,
296.
296, hold on. So a set of edges is called an edge cover. I'm calling it an edge cover if every vertex is covered. So we're covering vertices with edges.
Right.
Is an edge cover. A vertex cover is we're covering.
Right. So an edge cover is a set of edges to cover all the vertices, and a vertex cover is a set of vertices to cover all the edges.
Yeah. Okay. Sorry. The edge cover number.
Sorry?
The edge cover number is a set of edges that cover the vertices,
And
and the vertex cover number is a set of vertices that cover the edges. So that definition, although a little confusing, is on page 296. And what I'd like you to do is, so now what I want you to do in your groups is look at problem number 7.6.8. Okay, so find in particular II, find alpha, alpha, alpha prime, beta, beta prime, alpha, alpha prime, beta, beta prime for these four graphs.
Do we want to switch which one has the prime now that we switched vertex and edge? Or does that matter?
Oh, it does matter. I mean, if we're gonna use his notation.
Okay.
So the edge cover, hold on,
The edge cover
Edge
is the prime.
Yeah.
cover number is the prime, and the vertex cover number is the not prime.
And also it should be the order of those sets.
It's the order, right,
Just check these and then I'll put the time.
order, right. Okay, so once again, we're looking for sets of vertices and sets of edges. Hold on. Okay, so we're starting with the graphs on page 296. 296. So what are the four parameters? 296 II. What are the four parameters for these four graphs? So alpha, alpha prime, beta, beta prime for these four graphs. And then just to get you real excited, if you flip the page to 498, what's alpha, alpha prime, beta, beta prime for these two graphs? So problem number one.
So the vertex cover number of this graph, any edge that's adjacent to a vertex in your cover is covered. Okay, so if you are adjacent to an edge, you cover it. So this vertex would cover that edge. Okay, this vertex would cover that edge. It could. I mean, it would probably be smarter to pick that one because it covers all of them. The largest set, yeah, that makes sense.
And 0 for
So to cover all the edges.
I remember.
Oh, sorry. For A. So for, you did beta and beta prime.
Okay,
So
so
beta is 1 and beta prime is 5.
Why one?
Because you can just cover all the edges.
So you don't need to pick up the vertex that are on the other end of the edges? You don't really have an edge without a vertex on either
So you're
end.
just trying to cover.
so
So this
when we
vertex on
said about
this edge, so this one doesn't have to.
the
So you
edges
could choose
cover all the vertices,
Right.
cover the vertices, exactly. So the vertex cover number means the number of vertices that
So if you had
covers
one
all
like
the
this, you
edges.
would need
Right.
one.
Exactly.
Yeah.
Right.
So it's all the edges.
All the
And
edges,
then what you put
right.
for alpha and alpha.
Okay, so let's just make sure we're all on the same page. If we look at, what is this page? Oh, 310. Is this 310?
No, it's 296.
296. Okay, if we look at the star, let's take the easiest one. What may be the easiest one? Okay, so here is, just to remind you, we haven't used this notation in a while. This is K15. What's the order of the largest set of independent vertices?
Fine.
So in other words, the independence number, the order of the largest set of independent vertices.
So this is the largest set on
What was that? Five.
Well, this is,
Okay. What's the order of the largest set of independent edges?
yeah, those three.
And then,
1. Okay, every edge goes through that middle, that center vertex. So as soon as I have that center vertex, no other edge can be included in the set.
I can't find more than 2 then.
Okay.
Share vertex.
So beta is the vertex cover number, the smallest set of vertices that cover the edges.
So 2. So for these two, this guy.
When I say cover, it means that
Yes.
every edge contains one of the vertices in that set.
Sorry, my answer is just.
No, this one.
1. Okay, so the center point is a vertex cover for all 5 edges? What about an edge cover?
Any two, 3, 5,
5. We gotta cover all those vertices on the outside, so every one of those vertices has to be covered with an edge. Each of those edges covers only 1, so the vertex cover number, vertex cover number and the edge cover number can be fairly far apart. And if we look at K1N, they get even further apart for n bigger than 5.
keep thinking backwards.
Okay, let's do something a little bit more interesting. What about B? Take a minute. B, C, and D.
You need all of them but one?
I usually think about them as like little bars. So this part catches these two, and maybe this part catches these two. So you need a third to catch this one.
Catches these two vertices. This edge catches these two vertices, so I just need one more edge to catch him. So 3, okay.
Maybe there's a way to do it. I feel like there's not. You absolutely need this one. And then any other edge you pick, you can move that this one more.
Yeah, because we have a number left over. 2 vertices. 11 of them. We have an even number of edges.
2.
Yeah, I remember back when we graded this class, it was like, everybody had edge cover and vertex cover backwards. It was like, those are the worst points to take away.
Yeah. Sorry. My apologies. Okay.
Well, what's worse is they use different Greek symbols. Don't they?
Oh, never switch from that from beta. Wow. What did you got for, so do you have, I have
2.
alpha is 3.
What 3?
How many colors? 4.
Oh,
Not 3?
And alpha prime is 2.
Good.
And beta is 2.
Okay. Alpha plus beta.
And beta prime is 3.
Prime equal n.
Okay. And then on the house.
is it always flipped like that?
What do you mean?
So
Interesting.
big.
Oh, well, they're, you know,
This method
What
is
did you
just
do?
that.
What did you just do?
Hit the log off button. I was like, here, look at my blank screen, answer my question.
Can you see through that?
what do you think about
Alpha
this?
plus beta. Plus beta.
Is your alpha
Yes,
prime
that's-
matches your beta and your beta prime isn't your alpha? Or did it just happen to work out that way with the first two that we've done?
What were your answers for the first one?
No, because they're 5015. You should have a 0.
For which one?
Alpha prime.
So we're conjecturing
The first one?
alpha plus beta equals alpha prime.
The largest.
Ah, yeah.
Equals n.
Isn't that
Because
fair?
they're all touching
They're all
the
adjacent.
middle.
It's an identity.
There is a relationship.
But it's not.
Trust and
That's
believe.
not it.
He may not be that. Something about adding two
It's a
things
good
together
conjecture.
makes another thing.
Maybe it's
It
like,
says the
anyway,
alpha
Yeah,
prime
it's
and
on the
beta
next
prime.
page.
Oh, well, there you go.
I'm trying not to look ahead.
Here we go.
Hey,
Oh, here we go.
Okay. So what was doing?
Galli.
Galai.
Galli.
Ages.
That doesn't have anything to do with Galileo, right?
No,
Like
no,
the-
no,
Like
no,
the
no, no.
adjective form of his name or
No,
something?
Galai was
Smallest.
20th century.
Oh, okay.
3. Three also.
Seems right.
Okay. Tell me when you finish C.
Independent one， 最高是2个，没错。然后还只看到主要是3个。
Oh.
不行。 还有个发条规定，那有什么？比如说相乘相加这等于5+3，2+2，它的表现，这个去原来图的所有的规律都放弃了。
So how are you making out? Figure 7.6.3. Yeah, I want you to do that too. I mean, the ones on the previous page are just a little too simple.
Just agree on the little house. So we have 2 and 2 for alpha and alpha prime. And then for beta, I have 3 and for beta.
这个很像那小号码。
Vertex cover, so if you did one, so that you have查的然后 you have to do 1, 2, but then would that one be
还以为
adjacent?
第
Or
一
is
项
the
是
other?
是
When you're trying to cover edges. So if you choose this vertex, that covers these 2 edges. If you choose this vertex, that covers these 2 edges. But this edge isn't covered yet.
然后是那个
Oh, so that's where your third is coming from?
And then the same thing with the beta prime.
不是，我看微信上去，这个不习惯了。
Does that make sense?
Yeah.
And then I
是的，
said that edges to cover the vertices. So this edge will cover these 2. This edge will cover these 2. And then we need another edge to cover them.
Yeah.
Okay. Sometimes if I say it to somebody else, I might remember.
Right.
Okay, go for the tree. So anything that has degree 1,
Yeah, you
gotta
have
use
to.
that edge.
Yeah.
So all of these guys have degree 1, so we all got their edges. This one has degree 1, have to use this edge. 1, 2, 3, 4, go. The light bulb goes on.
I am truly blessed with divine knowledge.
Yeah, let's go with that.
Check out this fundamental truth of the universe.
It's so cool. You have degree 1, you have to use this edge. How many do we have degree 1? 5.
You might not, right? You might have to use more.
Right, but minimum.
At least that many.
Yeah, because if this was a longer tree, no, it wouldn't matter.
Well, this one's a good example,
Yeah.
right? Because you use this one, but there's not any more leaves, but you still needed more
Yeah.
edges.
So you have to use every leaf. Minimum number of leaves.
Right.
Okay.
Yeah.
It's a theorem.
Yeah, the other ones were just too easy. Let's just make sure we're all on the same page. For the graphs on the bottom of page 296, the star, we've done the star,
What was alpha and alpha prime?
okay? The star, what's the largest number of independent edges? Independent edges.
It needs that edge.
You explained it to me.
1. What's the largest set of independent vertices?
I get the credit for that light bulb.
5.
So anything with degree 1.
What about B?
Just need to see if you need any more.
Largest set of independent edges?
In that case.
Right.
2,
Largest set of independent vertices?
3,
3. What about C5?
Cycle 5.
2 and 2. What about C7? I know C7's not there.
3 and
觉得是
3 and 3. What about C9? What about C8? 4 what? 4 and 4. Four vertices. So a cycle is not too bad. We don't get cycles very often, but so Cn, the number of independent vertices is going to be n over 2. We know that notation. And the set of independent edges is also going to be n over 2. Okay, every other edge doesn't share a vertex. Just to remind you For C5, if I take every other edge, they don't share a vertex. Okay, so the vertex independence and edge independence, they're the same. What about Kn? Just Kn. What's the vertex independence number? But Kn, what is Kn?
It's like the complete.
The complete graph. How many independent vertices are there in Kn? One. Okay. What about independent edges? What does it mean for two edges to be independent? They don't share a vertex. So like for K5, for K5, how many independent edges? How many? No. In two edges that don't share a common vertex. Two. And what about K7? And what about K8? And K9? 4. Okay. So the complete graphs we know, by the way, number of independent vertices in a complete graph is always going to be 1. Okay? All right, so let's go back to, so the graphs on the bottom of page 296, those are pretty simple. Maybe. Maybe. They're simple. Okay, one more time. The number of A, that's a star, K15. Number of independent vertices is 5. Number of independent edges is 1. B, number of independent vertices is 3. Number of independent edges, 2. C5, 2 and 2. And D, I don't know even what that's called.
So alpha should always be 1.
So 5, which one's 5? Independent vertices, there's 5 independent vertices, but only 3 independent edges. Okay?
3 because
Okay, what about 298? Okay, really, we're working on, I'd like you to work on problem number 1 for these two graphs. So a maximum matching, a maximum independent set, a minimum vertex cover, and a minimum edge cover. Remember, I'm going to cover the edges with vertices for an edge cover, and I'm going to cover the vertices with edges for a vertex cover.
Okay, I think that's K7. So the number of independent edges is like, you can just go along the cycle.
Every other.
Right,
For a while.
because
Yeah,
you go along the cycle for a while, and then, you can't have any in the middle because it'll be connected to everything. So,
But how did she just know?
she's just following a pattern. Well, alpha's always 1.
I didn't know that.
And then alpha pattern is always the same as the cycle. Right, because that's how we got this. The cycle's over 2. Just divide by 2.
Oh, this guy is the lower end of us, too.
Right, well, and for K7, that should be a 3.
Perfect.
This one should be
Because 7 over 2, bottom end would be 3.
3.
And then for K,
It's just it's, yeah.
the lower end. And then okay, now we're supposed to do this one. I can't hear.
我知道你是为什么你想逃避小孩学校，然后你今天愿意逃避，你就写不到啊。只有这样，这是现实。
Wow, you all look stymied.
No, actually,我一点没有但是我是
Which one?
是有关系的。
Okay? Okay?
It looks like,
So how do you show that it's 5? It can't be 6. How can you show that it can't be 6?
I don't know how to do that part. That's what I need to know.
that's a hard part.
Pam, you,
I agree that it's 5, but I don't know how to show that it's
okay,
6.
all right. That's that's the hard part.
Yeah. So it must have to do with the degrees.
It can serve as a heuristic, but I think you can end up with graphs with low degree that get like bad with the independence number. So you could use it to look at a normal graph, but somebody like in computer science we call them your adversary. What's the worst case for your algorithm?
Okay.
So your adversary gives you this horrible case, and it takes you forever to figure it out, or your heuristic is just bad. But you have to look at, so the brute force way is to look at every set of 6 vertices and see that none of them
Every
do
set
it.
of 6.
Right, well that would be, if you can't find any set of 6 vertices that are independent, then you know the independence number is less than 6.
Which I couldn't find, but I can't promise you that I didn't miss something. That's the thing.
Right.
Is that I don't know if we lucky.
Well, how many vertices do you have? 10?
Okay. What is it?
You have 10 vertices, so 10 choose 6, it's a big number.
Yes, it is a big number.
It's a lot of subsets of size 6.
I'll probably getting one.
Well, you gotta have 4 too.
But you can do 3, but then you can't get any more.
These are pretty small graphs,
You can do
and you're still having trouble with these.
3, 4.
Not that you weren't supposed to.
You're saying real graph theory is hard.
I'm saying that it takes more. We need to develop some theory.
Yeah, so I'm seeing a lot of 4s.
Oh, okay. You're
But
trying
I
to
don't
get
see any 5. Yeah.
Guys, I think you want to prepare yet? Still working on what's.
You could look at the cycle 1, 2, 3.
Each cover of 5. In which one?
Well, I don't know, but
So these vertices are adjacent to everything that we just used in that cycle.
So that I have.
Certainly the best we could do is 5. That would be a perfect measure.
4, 5, 6, 7, 8, 9, 10. Oh, no, because.
To be smart about it, maybe we'll look at the loaded versions. This one.
See.
Okay, maybe we could get cute and use this one. I'm not super huge.
Okay, so, let's see.
I don't think we're
Break it
going
up
to
into 2
connect
cases.
here.
Okay, case number 1,
It's
A's
connected to the most number.
imagine our.
Right, well, so you might want to use that one.
Okay, so.
I mean,
Z is our
eventually you'd have to use it if you can find a 5, right, because we have 10 vertices. So you'd have to use it eventually. You might want to use it to connect to the hardest one to connect to.
Okay, now CY has to do matching.
I think 1,
You see?
2, 3.
Yeah, because
Okay.
C's.
No,
Yeah,
And now D is not in the matching.
gotcha.
Okay, so AZ is not in the matching,
4,
if
Okay.
one exists.
So then,
2, 3. No, because those were
yeah, the identities,
And then do the kind of the other case, AZ is not in the matching, then AX.
Vertex.
right,
Cover
and you just go through
Yeah,
elimination. Okay.
yeah. And then
The
the other
vertex
one,
covers a set of
same
vertices
kind of
to
thing,
cover
so
all the
now
edges.
you've got, I don't see any.
So this gets you a
degree
long
twos,
way,
So you gotta have
but
3
you're missing
So I
this
chose
edge, this
the
edge,
3
these
that are incident to
edges.
D. If you
Mhm.
assume any one is in the perfect matching, you can show that that's not the perfect
Right.
matching.
So Z seems like a good candidate.
So I definitely feel good about that.
the number of vertices to cover all
And
the
then the
edges.
maximum matching is you can
But yeah,
find
vertex cover is a
one
set of
less
vertices
than
which
what a
cover
perfect
edges.
matching
So
would be.
this one will cover
And show, and since you've shown that there's no perfect matching, that's the maximum.
every.
Yeah, it has to be maximum.
Or
Okay,
might
yeah,
all-
that makes sense.
For the
all of
independent
these two.
sets, I'm not sure how to
No,
show.
no, no, I keep going to vertices.
I'm not sure how to show there isn't one exists greater than the one that I've found.
Gotcha.
It doesn't cover these two.
Um,
Right, or
Jacob,
these two.
Jacob.
Did you catch all that?
So these seem like good edges, right? Because it also doesn't cover this edge, right? So you might want to pick these up too.
Which will cover this ledge.
Let's see here, so,
But it won't touch these two.
oh, okay, so what are the 4 numbers for this one?
So you can pick 2 of these.
So we want to do, let's just make it this. So we want Z, and then this one, this one.
它分的 match 是如果你可以买出来
Will not pick up this one,
So we got,
or these two.
okay, and then the largest matching.
I have now picked up this one, this one. Oh, but this one.
Okay, and then, yeah, and then based on
Right,
that,
well,
that's
these are getting.
Oh, yeah.
the other 2 are
And then Y will catch W. I mean, going to W.
Right, and we're going to
And then Vertex. So then I can't get it.
对，然后
So just back kind of 7 I agree.
unless you pick up X. Right, you pick up X.
怎么高级？
Okay, you,
These two.
so you're struggling with these, so let me give you some more things to look at.
But you will pick up
Okay.
this one.
So let me give you a few more definitions. A K coloring of G is a coloring. So you can think of it, if you don't like colors, I don't like colors, being colorblind. So you can think of it as an assignment of 1 through some number K. So it's a coloring of the vertices with K colors, or if you want 1, 2, up to K, so that adjacent vertices get different colors. Okay, so that's a K coloring. If you find the best K, the smallest K, then we would say that it's K chromatic, but we'll talk about that in a moment because I have another definition that we want to talk about. So if you had to guess, a K edge coloring
Incident edges are different.
Okay, so G is a coloring of the edges so that incident edges are assigned different colors. Okay, so K coloring, we're coloring the vertices, K edge coloring, we're coloring the edges. And now let's take a look at the map of the United States. So what I want to know is the, I'm going to say map, colorable with 4 colors. So in other words, we're going to create a graph. The graph is, I put a vertex in every one of the states. I put 2 states adjacent if they share a border. That gives me a graph. And I think I saw, did someone have that graph? Is that the graph right there?
Yeah.
Yeah, so you can actually create a graph. And then you want to color the vertices of the graph so that no 2 adjacent vertices are given the same color. And this is the result that I've talked about a couple times, that if we construct graphs in that way, where we construct them based on maps, then every such graph can be 4-colored. Okay, that's called the 4-color theorem. And we'll talk a little bit about that and some of the history. But not all graphs can be colored with 4 colors. Okay, so let's just make sure. So if I take K5, so K5, Okay, it can't be colored with 4 colors. Okay, obviously. Is that clear? Okay, now what's really strange is, now try and draw K5. Try and draw K5. I'm stocking you up on problems to play with over the weekend. Try and draw K5 with no crossing, with no edges crossing. Did anybody try that? I think I gave that last class. Could you do it?
I have one that I couldn't get out of the way.
Okay, so it comes down to one last edge that you have trouble. So try it, and then let me again. I think I mentioned this the other day. What happens when we draw it on the donut?
Oh, yeah.
Okay, so one more time. So I'm going to take 5 points, and why is the donut any different than the sphere or the plane? I can to go from this point to this point, I can sort of go down the edge, and now I'm on the bottom of the donut, and then come up over here and come. So I have a little bit more leeway. Can you draw a K5 on a donut so that no edges intersect? Okay, I suggested you get a donut or you get a bagel, and or if you, I've seen styrofoam donuts, and use toothpicks and then put some string around it and see if you can do that. Okay, all right. So we'll come back to that. That's for probably later next week. So I've got this idea of coloring. So how'd you make out? How'd you make out on these graphs here? So one more time. So I'm back on page 298. There's no perfect matching for either of them. Okay, so I'm looking at the top of 299. Does G have a perfect matching? You say no. What is the size of the maximum matching? How many edges are there in the largest matching? Anybody? For A or B?
Yes, the maximum matching.
Maximum matching.
No.
4 and 5.
4 and 5. Which one? 4 is on the top and 5 is on the bottom. Okay, I'm looking at, by the way, I'm looking at on page 299, I'm looking at part C in G. Find a maximum independent set. You think 6 and 5. 6 and 5. Okay? How would you get 6? Oh, say that again? Oh, are those two non-adjacent?
Right. Okay, I got you.
5? 5 and 5. Okay. I think that sounds right. Okay, so I want you to, so again, over the weekend, I want you to find a smallest vertex cover, a smallest edge cover. If you've done it, that's great. I want to look at number 2. Let T be the family of all trees of order n. By the way, did I ever show you how many different trees there are on, say, 20 vertices? How many trees do you think there are? How many different trees do you think there are on 20 vertices? 40? Thousands. How about hundreds of thousands? Maybe.
See you, raise you to millions.
I don't know about millions, but okay. So let Tn be the family of all trees. What's the largest value for the independence number? What's the largest value for the edge independence number? What's the least value for the edge cover number? What's the least value for the vertex cover number? Maybe we should start with just A and B.
On a donut. Well, I mean, you can-
And I'll let you know that A should be pretty simple.
and,
The largest value of the independence number of a tree. N over 2? N minus 1. There's a big difference between N over 2 and N minus 1. Well, so what would N minus 1 be?
It's like all the other vertex connect to one.
Yeah, that's called a star.
Oh.
Yeah, so what's the independence number of this tree? By the way, this is a tree, right? What makes a graph a tree?
No circle.
Connected,
No
no cycles. That looks pretty connected, and there's no cycles. So what's the independence number? In this case, 6, but I can just keep going, right? So this is K1, N minus 1, so N minus 1. Okay, what's the largest set of independent edges that you can have in a tree? Let me stop. What's the largest set of independent edges that you can have in this tree?
2.
One.
Well, it's not clear where you're.
So in fact, this is a pretty sparse graph. It is connected,
So it connects to.
and it has a very small set of independent edges. But it has a very large set of independent vertices. What's the smallest set of independent vertices that you can have? One more time. There's a large set of independent vertices. Everybody sees a set of
So
size
you have an
n
edge that
minus
goes
1.
around the donut and back to itself.
Can you give me a tree? Remind me, what's a tree?
So
Forget these things. Tree is
those
connected.
are loops.
and no cycles. Okay, so connected and no cycles. That certainly is connected and contains no
So
cycles.
like you have 3,
What's
you
the
have the 4th, because each one is degree.
smallest set of independent vertices that I can have?
Edges, and then the 4th one comes around the bottom.
Well, if you're making a
On
loop,
n
you count
vertices.
one going out.
So the tree has n
same
vertices.
edge again coming in, right? Like, for example, these 2 vertices are not connected to each other.
Maybe you should even start with 6 vertices.
And in a K5, they're
They
all.
are.
totally-
What's a tree with a small set of independent vertices on trees of size 6? 4 is too small. Although 4 might give you the answer. So you think
On 6, is it 3?
the smallest set of independent vertices on a tree of size 6 is 3? And can you give me such a tree?
Make a path.
Oh, a path. So what about a path of length n? Sorry, a path of order n. Order meaning the number of vertices.
Minus n over 2? Minus n over 2?
What minus
Just
n?
n over 2.
What?
N over 2?
Just n over 2. But what if n is odd?
Lower limit.
You sure?
No.
Take a P5. Take P5,
To be perfectly honest, no.
or even smaller. Take a P3. How many independent vertices does P3 have?
2.
Okay, so What do we think? N what?
Plus one.
N plus 1 over 2. So n plus 1 over 2. So that's something we need to figure out. What is the, well, see, I know a lot about trees. Trees are bipartite graphs. And you have to remind me, what's a bipartite graph? Bipart.
2 partitions.
2, you can partition what into 2?
2 partitions, I didn't hear what you said after that.
I said, that's it. I said bipart.
Oh, 2 parts.
What's in 2 parts?
Oh, the vertices.
Vertices. I can partition the vertices into 2 parts where each of those parts are independent.
Independent.
Okay, so if I have n vertices, then one of those parts has at least n over 2 vertices in it. Okay? So in fact, that goes for bipartite graphs, not just trees, but every bipartite graph has vertex independence number, just independence number of at least n over 2, and in fact, it's n over 2 ceiling function. Okay. Again, bipartite means I can partition the vertices into 2 independent sets. Okay, back to problem number. Does G have a perfect match? What's the size of the maximum matching in G? Okay, find in G a maximum matching, a maximum independent set in G. So this goes A and B here. G is this graph here on page 298. Graph A and graph B. The largest matching is, what do we say?
I think I can see 6.
4 and 5?
Yep.
Okay, largest independent set? 5 and 5? Minimum vertex cover. So this is, it now gets, we're gonna pick some edges out. So a vertex cover. Smallest number of vertices that cover the edges. Smallest number of vertices that cover all the edges. And notice you can cover some edges more than once.
Maybe you can do that.
You just need to be sure that you cover all the edges.
Can we have a perfect matching? Sorry.
But he might have been answering. So the maximum matching is.
Give maximum matching. Right. So therefore the edge cover number has to be at least 6. Well, we found one at 6, so we know it's 6.
Got one at 5.
And then maximum independent set is alpha. And then what's our color?
Vertex.
So that's beta.
Yeah.
Okay, that's 5. Okay, so we answered these, but they didn't put the Greek letters in. Okay.
We're not ready for Greek letters.
So I have to guess what it is. She's doing
I got stuck up
the
in
K5
donut.
on the donut.
She's doing.
But she can do it in color, so it's very cool.
Okay.
We're gonna
All right,
use
so
colors.
here's what I want you to do. I want you to, that's where I'm going to start on Tuesday. So page 299, I want to finish 1, 2, and then 3. And then we're going to move into chapter 8. So vertex colorings, and we started a little bit with a K coloring of a graph, and then the K chromatic the chromatic number. So we'll talk a lot about coloring. In fact, I still have 8 minutes. So I'm gonna jump to page 311. Okay, so here's a graph, a very simple graph. I want to color the vertices of this graph with as few colors as possible because we're trying to be stingy. We don't want to be switching pens all the time. I want to color it with as few colors as possible. so that no two adjacent vertices are given the same color. So again, I'm on page 311. It's a very simple graph.
Wouldn't it be the same as the independence number? Isn't it three?
So an independent set, you can give them all the same color.
Oh, yeah, yeah.
But,
I can't reduce it.
right, so, you know, that's a way to fill in one color, but like,
Okay,
you need
so
to choose your
red, red,
independent
red.
sets so that
There you go.
you can do it with the fewest number of
如果
colors,
是
So you
right?
could do red, red, red,
如果是
two.
vertices 的话，就是 independent
Um,
vertices 有几个？
well, you have a problem here.
Oh,
Red, red, you can't do that.
okay.
So the independence number of this graph is actually
Yeah,
not
I
correct.
see
vertices
that.
和 independent set 找到找到几个 independent。
All right, let me ask a real simple question. Can you color the vertices with 5 colors?
Yeah.
Yeah.
Okay, so we can always be very inefficient, right? We can always color a graph with n vertices with n colors.
But this, either one of these could be this one.
Can you color it with 4 colors? Remember, when I'm coloring it, I don't want two adjacent vertices to have the same color.
So these two could be the same.
Okay, so I can color with 4 colors.
So what's your color?
Red,
Can you color it with 3 colors?
yellow, blue.
Okay.
So three.
I see a yes and a no.
What'd you say? Did you say three?
3.
Yeah.
You can color with 3 colors. Can you color with 2 colors?
I can't.
Okay, so why can't I color it with 2 colors? Because there's a triangle, exactly. Because if I look at, we can look at small pieces. I have a K3 here. And the vertices of this K3 must be colored with different colors.
Across the donut hole.
Okay, so we do have some bounds that we can generate based on this. Okay, so if you turn to page 312, it gives you, we can color 5 colors, easy. 4 colors, pretty easy. 3 colors, also pretty easy, but not 2 colors. Okay, the same would, I would ask you to do the same for 8.2 and 8.3, but instead, can you color the edges? How many colors do you need to color the edges so that no intersecting edge is given the same color? So if I have 2 edges that share a vertex, they're given a different color. One more time. I want to color the edges so that edges that are incident to a common vertex are given different colors. Looks like there's 6 edges. I bet I can color it with 6 colors. Three? You think 3? How many people think 3? Okay. How do we color with 3?
This one, these two, these two.
Put the numbers up. 1, 2, 3.
Puts it up where she can reach it.
Oh, wait, whoa. Ah, there we go. Very good. Okay, so notice this. Oh, look, the 1s form an independent pair of edges. They're independent, they don't share a vertex. The 2s form an independent pair of edges. The 3s form an independent pair of edges. So in fact, just like when we color the vertices that are colored color 1 must be an independent set of vertices. When I color edges, the edges that are colored the same color must form an independent set of edges. So we have this relationship between the coloring of vertices and the coloring of edges, and we'll see how they are tied together in the next, in two classes. So next Thursday, we'll see a relationship. Any questions? You have a lot of homework to do. What's so funny, Dave? So you have a lot of problems to work on. Okay, so you have a lot of graphs, but you should be drawing graphs on your own. Oh, let me look at what happens when I draw the graph like this. What happens if I look at, don't take nice graphs. Take graphs that are ugly and see if you can figure out the minimum number of colors that you need to color the vertices, minimum number of colors that you need to color the edges. Questions? And eventually we'll get back to the map coloring problem. Have a nice weekend.
So like, if you do that knitted thing, where you get the rubber band, and it's like on a, that's what
Or you make like a, yeah, or you can make a cookie.
like that.